Okay, so before the break there, we looked at dates and times and got a few other things on the list here. Dates and times were the last thing that I wanted to make sure was in class before at some point this semester. So everything else is just kind of in this odds and ends section, things that I think will be useful for you. And I believe quite a few people were in the cybersecurity program, weren't you? I see like a show of hands. How many of y'all are one of the little icons or something? I see a couple hands popping up there. 3. So that's almost half the class today. So I think I'll go to that one first. So we're going to go through anything super fancy here. Okay, yeah, there's another hand there. So that's half of the people in the call today are in the cybersecurity program. So one of your big deals is securing data. So let's talk briefly about encryption. So we're not going to do super complicated encryption here. Just kind of look at the basics. Right? The idea of encryption is disguise our data. We hide it so that people can't readily see what it is, right? The basic old versions of encoding, like if I have my name, we could make up some sort of cipher to change that into something else and say that maybe let's do the alphabet backwards. A is Z, B, C, D, E, F, G, H, J, K, that's 11, 12, 13. That should work, right? Z, Y, X, W, V, U, T. It's hard to do the alphabet backwards. I should probably go to the end. S, R, Q, P. There we go. So we can just replace one letter with another and hide what the words are. So replace C with an X, an H gets replaced with an S, R, find that on our list, switch that over to an I. I was calling my name. Oh, then I becomes R, and S switches back to an H. So some sort of encoding. The data is in a different form, but unless somebody knows the cipher we put together, they're going to have a hard time figuring out what that means. That's one of the basic ciphers. So anybody that breaks codes is going to figure that one out. Anybody that's had experience breaking codes is probably going to would recognize that one almost immediately.
So we encrypt that data, so we make it more complex, so it's not easily.
So now somebody has to know how we hid the data, how we disguised the data, in order to get back to what the actual, like in this case, it's showing my name. It looks like just a random. So it's like letters, but it followed this pattern so that we can get back to it, right?
Yeah, plus I'm a sports person, and so I would like have this as an analogy of like having your own playbook.
Yeah, like basically.
Have your unique playbook to where the other, which is the hack or their team, right?
Yeah, so we're going to look at the basics for that. So to do this, we would usually use, in a computer, we'll use a math function, which modern encryption techniques get very, very complicated. So for our example here, we're going to go with the simple one. I'll make a note up here, simple for example. something that you would have seen in like 7th grade math. That way we can follow along with the pattern when we go code it up. But the key point, the biggest thing is we can't just use any math function. Because some functions don't go both ways, right? That's a good example. Oh, squaring a number. It kind of seems to go both ways. If we just take some value, like maybe our ASCII value, and square it, we get something. But if we look at basic numbers, we plug in a 2 and square it, we get a 4. We plug in a -2 and square that, we still get a 4. So going the other way, that it's not a direct relationship, right? If our
Yeah,
encrypted
plus I
data
learned
says we
in
have a
plus I
4,
learned in
we don't know whether we came from a 2 or a -2.
yeah, plus I learned in algebra that, if you square something, twice, regardless of the original number, like it will be a positive.
Yeah. Yeah, and there's a lot of things that are like that. We could write more complicated functions that still come back to, we can't really undo them. So we need
Exactly.
something that goes both ways. Math function that's that we can undo. So some of y'all might remember in your math classes the word invertible. We need something that's invertible. So for our example, I was thinking of just like a simple line. It'll show the concepts of what we want to do and the steps we would need to carry it out. So obviously modern encryption gets very complicated, so we want something simple to work with. So yeah. So do 3 times some ASCII value. I'm put a little star beside it because I'm going to do one extra step, then maybe -18. And that'll give us our encrypted data. So we'll take in some message, and all of that message, the string of characters, remember every single character is internally represented as an integer, Unicode or ASCII code. So we can take that number and plug it into a math equation and get some different value out of it. And store it that way, so if somebody looks at it, it's gibberish compared to our original message, right? They won't know what it is, but we carefully designed this function, a simple line, because we can go the other way. Then when we want to decode it, the ASCII value we'll get from each character would just be solving for that algebraically. So if we add 18 to that, get our encoded value plus 18, and then divide by 3, we'll get us right back to that original value. So that gives us a way to encode and decode our data, so it's not readily apparent what it is. I went back and forth a couple times doing this morning, getting ready, in both Python and Raptor, and the Python was a mess just to look at directly. So even though we just looked at something in Raptor, and I kind of like to switch back and forth if possible, to do this in Python directly and jump right into Python with this looked like a mess at this level of course, the introduction level course. So I'm gonna do the flow chart first, and then we'll quickly type. Then we'll turn around and type that up in Python with the same thing. But we just want to talk about the basics of encryption, because once we have this idea in place, we need to put that into an algorithm so that we can turn our data into that and then get our data back from that. And I probably could have brought in the example from when I was getting ready this morning in case I get something awful.
Did you save that one?
talking and typing. What's that?
Did you save that example?
The one from this morning?
Yeah.
Yeah, I printed it. I printed it out as a flow chart and then did that. But we're getting ready to go through the same example here. I was just thinking that I'm going to be talking and typing at the same time. So there's a good chance I'll make a mistake here doing more than one thing at once. So it probably would have been helpful to have brought that other example in with me. Yeah, to save it, I just printed out the PDF from it, and that way I can open it anywhere if I need to refer back to it. So a couple things we'll need here. And the thing that made it look a little bit better in Raptor was the ability to do submodules and break it up in pieces so that it's not all there at once. So first thing we want to do is get some input. So I'll add another little subchart. Well, normal, clear the console, get all the junk out of the way whenever we go have things printing out. And I'll create another subchart here called inputs, which again, the subcharts are just to kind of clean it up. So yes, create a new one. And we'll ask the user for some sort of message to encrypt. Enter a message here. And I'll just call that message to keep it straight. Then on the board, I was writing that little asterisk beside the ASCII. So I'm going to add one extra little step, which is very, very common in modern encryption, that we also use a salting value. So before we encrypt our data, we call it salting. We flavor it up, decorate it, add a little bit of flavor to it so that it's a little bit different before we even encrypt it. Just one more step along the way. I'm going to call that a key here. We'll use it as a key. Enter the encryption key. And the idea is that even after decrypting the data, you still have to know that key to get it back in order to get it the final step. If somebody
can use a common-ish encryption method and still have it be different.
Yes. Because
you don't have the key.
Yes. Yes. So I'm calling it key here.
You can guess an encryption method.
But yeah. Because the encryption method has to be a particular thing. And modern encryption methods would be a lot fancier. You should really be using matrices that we can pull an eigenvalue out of and then multiply by their transpose to have something symmetric. So we can do a spectral decomposition and use some much more complicated math. But the general idea here is the same here. When
I talked about the lava lamps with you, didn't I?
Yeah, stuff like that.
Yes, it's really, really cool.
So this key is, I'm calling it a key, but it's that last little step to unlock the data after it's encrypted, which is really more of what we would call salting the data. So we'll get those values, and then we need to sort of do things with that whole string. So I'm going to make another little loop here. Well, I'll run this along the way. We'll call this encrypt. If I go ahead and run it, and see, we get a message. So maybe we're going to encrypt the string hello, and then some sort of key to turn it, to twist it around, which is a salting value. So I'm going to use salt. And then that gives us two separate sets of numbers that we would have to know. So like a common salting value would be related to the user's password, so that only a particular user can get their own data back because it's based off their password or something. But then we'll combine our ASCII code from both values in order to find the one we want. So is first off, we need to salt the data. So I'll make a new another subchart called salting, where we'll flavor up that data. So it was mentioned, at least briefly, that a string is always an array of characters. So we can always work with a string as an array. So if we set up a loop, our normal looping process, set an index equal to 1, loop through and go until index is bigger than the length of that message string that we want to encrypt. Then on each pass, we'll increment our index. We'll set index to what was already stored in index plus 1 more, and just hit every little item in that array. Oh wait, this is the key. This is the salting one. So we'll do the key length of the key string. And what I'm going to do is come up with another number to change the ASCII code from its original value before we even go through our function to hide it. So I'm just going to take the sum of them, mod 16. That'll give us just a random number so that we can change all of our ASCII values, and then we encrypt the changed version. I'll call it KeySum. We'll start at 0. Oh wait, this will be the actual key. Uh-oh. No, I don't want to type KeyString. Okay, I'll call it KeySum. It won't let me type just the word key for some reason. And then on each pass through our loop, we'll just add the next ASCII value from that secret key that the user types in. So we'll set KeySum equal to whatever was there plus, and we have these two methods, to ASCII, and we'll pass in a character. So if we pass in a letter, that'll give us back a number, and to character, we pass in ASCII. So if we pass in a number, that'll give us back a letter. So we'll want to use those a lot. So that KeySum will increment by that to ASCII every time, with whatever the next letter in our key string is. So key string, whatever the next index is. So just keep taking that, turning that into a number, adding it up to that sum. And since in most cases, if our data has to be a certain size, right? So usually we don't want those growing too big. So after we get done, then we'll take KeySum and set it to whatever it was, mod 16. That way it's only a number between 0 and 15. And we don't accidentally give ourselves a really big number that won't, that's hard to work with. But it's a value that's not super easy to guess, and obviously better encryption, we'd want to make that harder and harder to guess. But for our simple example, we'll just use it. We'll find a small number based off a secret string the user enters. That might have been a better name than key. Call it secret string, because we'll need that to hide our data. So now when we run this, type in some sort of message and enter a salting value. I'll just put salt again. Here we take salt and we'll grab all those ASCII values, add them up together, divide by 16, and then we have this 4 here that we can use to change the ASCII values of our original message just a little bit more before we encrypt them. And then basically we'll do the same thing for our other to encrypt it. So I'll make something called encrypt. And it's basically going to do the same thing as this. So I'm going to copy this and paste that in. Get rid of those parts. So yeah, basically back to the origin, just a basic loop through our array of characters. Only this time we want to loop through that message. And on the way through, I'll add it as a comment. We want to do this. So our encryption value is going to be 3 times the ASCII character we're looking at, maybe plus the key, and then subtract 18. Whatever the word, yeah. So 3 times our ASCII value, which the key is just, the salting key is just there to change it a little bit, minus 18 will give us a different number. And then we can load that number into an array on each pass. So I'll make an array called encrypted. It's going to be an array. So as we look at different indexes, that's going to be set to that equation just wrote here. 3 times 2 ASCII. I should do this in a couple steps. Let me add one more thing in here. So let's set something called data point equal to that 2 ASCII of our message, the current character we're looking at, plus our key. Whoops. KeySum. So that'll just change that a little bit, and then we'll put that into our function, which is written on the screen. I don't know why I keep pointing at the board. So we'll set, I don't know, some array, or maybe call it encoded. The next index in there will be 3 times that data point minus 18. And that'll fill up an array with a bunch of numerical values. Then we can print it out. So set up another loop. The standard for an array, we initialize our index, set index equal to 1. Keep looping, and every time we'll set index equal to whatever was already an index plus 1 more. And we'll go until index is bigger than the length of that encoded array. So once again, we see that same thing for walking through our whole collection. And this time I'll just print it out. Put it in a couple steps. So print out encoded. So I'm going to print out this word like a label and then uncheck in current line. And every pass through the loop, I'll just add on to that line. So I'll put the next thing in the encoded array, the next index plus some space, maybe 3 spaces. That way we can see it a little clearer. Oh, with no line break, so uncheck the line break box. But there's no line break, so afterwards, then we need to print out something that has a line break. So I'll stick some quote marks there and then in the current line. So not printing anything out, but this one includes a line break. So now we should see some encrypted data. So if we enter the string, I guess standard message for testing things, hello world. And we need some sort of string to encode that with. So like some secret message that nobody else would know. So like maybe call it teddy bear. Or go through, turn that teddy bear value into a number. Oops, I didn't mean to go up that far. I'll go not quite full speed. And you can see then it turned each one of those numbers or each one of those characters into a number. And well, it's not ASCII code anymore because ASCII code only goes from 0 to 255. We've got some 300s in here. So it's clearly not the original form of the data. So if somebody was looking at it, they might have a hard time, they would have a hard time figuring out what that original message was, right? So we need to go, but the thing about encryption, if we do something that only goes this far, we didn't encrypt our data. All we did was lose our data, right? We messed it up if we can't get it back. So encryption has to be something that we can get back to from. So like in this example we're using, a simple line with two variables, hopefully you recognize that from your math class, that gives us something that we can solve for either variable and kind of go both ways. We can go back and forth. That's, yeah, the most important step in encryption is being able to decrypt our data. So after we do all that stuff, we come over here and make another subchart for decrypting. So I'll create something called decrypt. And it's going to be a lot like encrypting. So much like it, I'm just going to copy this code. I have to make it small to copy all of it. So we'll loop through again. Although this time we want to loop through our encoded data first. And the math we're going to do is changed. Because we want to do the opposite of this. Which basically means we need to solve for this algebraically, right? So going through our algebra steps, this minus 18. If we want this value by itself, we have to work backwards to it. So this minus 18 would become plus 18 on the other side. So encoding plus 18. Then we need to divide by 3. So I'll wrap that in parentheses, divide by 3. And we added the key to salt our values. We need to subtract that key to desalt it. Whoops. So that gives us an equation that will take those numbers, which seem randomized at this point, and turn them back into the original data. So each pass through will do this calculation. Set this somewhere where I can see that still. So we need to set a decoded array with a certain index. Actually, it's going to go right to a string here, isn't it? Let me cancel that. We can put it, we'll put it right back in a string. Decoded starts as an empty string, and then we'll keep adjusting it. So decoded is going to be whatever was there plus this equation to undo that encryption we did, which has our encoded array, the current index of it, plus 18, Then we'll divide that by 3 and subtract off our key sum. And I'm going to wrap all of that in another set of parentheses to make sure that gets done. All of the math gets done first. And then we'll just keep looping around, decoding what each one of those numbers is, adding that to a string. And then I guess afterwards we can just output that string. So probably don't need this other loop. Print decoded plus our decoded string. Don't need that output. So, well, for one, you notice there was a lot of copy and paste there, right? That often shows up when we're putting together encryption stuff because they're going to be very similar when we go both ways. So now I can give it a check. And another thing that I may not have said a whole lot this semester, did you notice how many times I ran that along the way? I didn't just go all the way to the end and then check to see if it works. A good rule of thumb is every time you can run a check, go ahead and do so. So I'll enter the message, hello world, our normal one. I'm turning the speed down just a little bit slower so we can watch it through the flow chart. We can turn that back up. And then some sort of string to encrypt it. Maybe a blue fish. So it figures out that extra little value that we need. And normally salting would be something very unique. Like it would be based off part of the user's password or something. Like the last 4 characters of their password. So you have to know that, and then only that user, or you have to know the last 4 characters of that user's password in order to get it. Is that filling up? Okay, yeah. So we have our data encoded. That message, hello world, now looks like this, HELL. Since we know what it is, that 312, we can see is that's the repeated O, the repeated L's. And then 87, 87, 87 is apparently the encrypted version of those exclamation marks. Oh, whoops, I forgot a step into the decoding. I think it worked right. It didn't crash, but we need to get back to ASCII code, right? Back to our data. So whenever we do all of this, oh, that's why it seemed like I was missing parentheses. So that gives us a number, and let me put it down here so we'll see it. So we have these two. So if we have a character, one of our letters, and feed it into this to ASCII method, we'll get back a number. But we can go the other way. If we have a number and feed it into this 2 character function, we'll get back a letter. So all of that, we'll do that math, feed it into this 2 character function, and then add it to the string. I'll try the same one again. Hello world. I'll do red fish this time instead of blue fish. And here it just goes, well, we've already talked about what it is doing. Just going through and altering that, kind of like this cipher we wrote up here, which used a different symbol or a different number to represent the particular value we're trying to hide or make it hard for somebody else to see. And notice this time it's different because of that key. Our double L's are 321, and that exclamation point is apparently 96, 96, 96. So that's the basic idea of how we would hide and then retrieve data, or the basic idea of encryption. We get our data, for example here, just a little message. Then we run through this math equation to change those ASCII values into a different number, so that somebody can't just look at it and figure out what ASCII code it is. And then that's the one we would store in a file or something. Then when we read it back from the file, as long as we know that key, we can run it through this other little math equation to turn those numbers back into the original message. Obviously, modern encryption is going to have much more complicated algorithms and things like that. Does anybody have any questions about the idea there? The basic
I don't have any
concepts.
questions. I just thought it was pretty cool, pretty neat.
This looked like a mess in Python. I switched over to this.
I couldn't imagine it in Python.
Yeah, because we have to turn it into lists and stuff. I can show you.
Yeah,
I can show you the code. This is.
it's easier to put up here.
That's probably, instead of going through all that right now, because so here's from when I was getting ready this morning. It might be slightly different, but just so you'll at least see it somewhere, I'll open it with Adam. So we have to, and you're probably used to taking your input and turning it into an integer or a floating point number, but here we can also turn it into a list directly.
Oh, okay.
The key thing to look at, I guess this is the only point for transferring from that flowchart over to Python.
Order C.
Or turns a character into a number. I don't know
I'm
where
actually salting it.
yeah, I don't know where they come up with the or. So there's the salting, and then the encryption, same thing. So ORed turns a character into a number. I don't know the origin of that, so yeah, that I guess it's like ordinal, maybe, but whatever it is, ORD will give you a number from some Unicode string, and CHR goes the other way. CHR, and we give it a number, and it gives us back a character. That one makes a little more sense. Those are the key points, but you can see it kind of looks like a mess. There's lots of lists and things. The logic is exactly the same as what I did here. Those two key points, I can put it in the flowchart here because those would be the two things that you're probably not familiar with. Let me add a comment here. Comment in Python. Cast your input into a list. So it looks like list, input, whatever the prompt is. Hopefully that makes sense. And then when we encrypt stuff, put it here. Oh. Comment in Python, ORD character gives us ASCII value. Whoops. Decrypt in Python, CHR of a number gives us a character. from ASCII code. Otherwise, the logic would be exactly the same. So you can take these flowcharts, looking at the loops and the inputs and stuff, and translate to Python. It came out as kind of a mess when I was thinking about doing that, getting ready this morning. But I know a lot
The
of people are
structures are
heading
the
towards
same, but the way that
cybersecurity.
they're
Sorry, what was that, Tyler?
the structures are the same, but the way that they are, I'm trying to think. The way that
Yeah,
they're
the syntax is
implemented are
different. I guess in
Yeah.
Python, you enter the loop when the statement is true and leave when the
Exactly.
statement is false. But those changes that you all have already seen. So those should be easy adjustments. But I know a lot of people in the class are heading into cybersecurity, so I wanted to make sure that was a, oh, wait. Let me save that and then upload it to the chat room. Okay, so make sure you grab the one that's 32.44 kilobytes. Whatever those last few steps were made a big difference. But a lot of people are heading that direction. So that was, yeah, that was the one I was thinking should probably be first on the list of odds and ends to know those concepts. Obviously, modern encryption is much, much more complicated algorithms. The math functions that we use for modern encryption do not look like the stuff we saw in 6th or 7th grade math. It's more like stuff you see in 400 or 500 level math classes, graduate level math classes, because, well, harder math function means it's harder for somebody to figure out that function, right? That simple one we did, somebody could probably figure that out before long. They just need a couple starting points to kind of guess it. So more complicated math functions, but that's a basic idea. The rest of that, looping through our data and changing character by character or number by number, changing what it is, one little piece at a time in those loops, that's the same for the more complicated encryption algorithms. All that would have changed is those assignment statements for how we change our data. But that takes us up to about 3 o'clock. That's about the time I was looking for. Any questions about either of those things from today? Dates and times, that's an important one, obviously, because we're humans. We want to keep track of everything. When was stuff done? When is stuff due? All of that sort of information. And then encryption, because a lot of people are heading down that path. So that's something relative to where you're going instead of the arbitrary like payroll calculators. Because if you're heading into cybersecurity, you're probably not going to write a whole lot of payroll calculators. That way we see something useful.
Quick question. A good way to use a delay or time in my game would be maybe a rock fall. And if you don't move or click a button by the time it happens, it
Yes,
happens and then game over. Okay. Maybe
That
that'd be a more fun way to do it.
yeah. I just wanted to make sure. I just want to see that you understand the concepts of how computers keep track time, and that we have it in pieces and have to put it back together into human time. We basically have milliseconds and then have to use math to turn that back into the human standards of time.
I want to make it into 10, maybe 5 seconds. Not make it too fast. Maybe hit space bar.
Yeah, that'll be a great place for a timestamp. And
okay, sweet.
I'll be pretty generous about those. I just want to see it somewhere. If you can't find anything else, just put it in, throw a date in the output. Like
I'll do that too.
I'll
put it actually.
Yeah,
I'll put out exactly what you said.
I'll
This
make
day happened on this day.
Yeah.
I'll just make it in my for me, I don't like know much about Raptor than what we learn about now. So it's just kind of just like having that as an output, and it's just like the time completed for this was on this thing, and it's just like
that'll work. Yeah, you could throw it in the name of the poem, Keegan.
Oh,
Just-
yeah, that's a good idea.
As you generate it, just a way to keep track of your of the poems the computer generates.
Yeah, I might make that the final line.
That'll work.
Yeah, I might make
Yeah,
this
like,
make it a
artist signing
final
it.
line.
Mhm.
Yeah, plus mine is like not like mine is gonna be simple enough to where it's not gonna be complex as like anybody else's, but it's still gonna be fun where it's like repeatable. You know,
Yeah.
it's like repeatable fun instead of just going through like, and instead of just like, drawing a character and everything, like, I want to do something where it's like repeatable and
I'm hoping you all are enjoying these projects because I know sometimes it gets stressful and gets frustrating. Programming's like that, but I really enjoy it. I feel the same way about programming as I do like other artwork, playing music or painting pictures.
Exactly.
It's
I have to be
it can
the
be
muse
enjoyable. So
kind of
hopefully,
calls
I'm
to
hoping
you.
y'all are enjoying that and feeling that, at least feeling that a little bit. But now's a great time to work on those. We have an hour and 40 minutes left on our scheduled block of time. Please use that productively. Be a great time to go work on your projects. As always, I'm going to be sitting here till 4:50 in case anybody has any questions. Ready to jump back on a Zoom call immediately because we have to end the Zoom call to get the videos. But as always, text messages and Ivy Learn messages are the two things that make noise on my phone. So from now until 4:50, I'm just going to be sitting here ready to jump back on a Zoom call and answer questions if you have them. Please use our time productively, right? This block was scheduled for our stuff. I teach more than just this class. So if you have questions in other classes, obviously at this block of time, anybody that has questions about our class has to come first, but I can answer questions from other classes as well. But please use our time productively. If you have any questions, let me know. Otherwise, I'll see you on Wednesday and we'll continue with odds and ends that I think will be useful for you all. So see you Wednesday.